And feel free to interrupt me if you have anything unclear or you have any questions. Um, so the content of starting from today and the following classes will be arranged as follows. So we are going to firstly talk about different techniques that are commonly used nowadays for robot learning, such as reinforcement learning, behavior cloning, or visual imitations. And by the end of the semester, we also will present case studies or research projects that use these techniques. So the purpose of this lecture is to introduce you some basic and useful knowledges and to help you understand where you are presented of the case studies on locomotion navigation, so dexterous manipulation. And reinforcement learning and sim-to-real are kind of very commonly used in locomotion and manipulation. So the topic today will be closely related to that part. And in today's lecture specifically, we are going to firstly review some basic reinforcement learning or RL basics. So RL is a prerequisite for this class. So hopefully you already know most of the concepts. And then we will also talk about some of the attempts to applying RL to robotics and their limitations, their challenges, and why they do not immediately work. And after that, we'll also take a small detour to talk about one important line of development, which is the simulators, and which we talk about simulators and also together some algorithmic improvements and also engineering effort that finally makes RL for robotics works nowadays. And finally, we will also present a small case studies on OpenAI's dexterous hand together with high-speed drone racing to talk about how we apply this concept on real-world robotics. And let's start from the firstly reinforcement learning review. Our target is to have a robot or an agent to interact with the world and by receiving feedbacks from the environments. So from the environment feedback, the agent can adjust its behavior accordingly. So this assumption or a simple and reasonable mathematical model we can have is something we call Markov decision process. And in this formulation, the environment will provide the agent a collection of states that defines the environment. And the agent will, according to this state, perform some kind of actions and send these actions to the environment. And the environment, given the current state ST, and also receive some agent's output, the state will change. And how it changes is defined by this transition dynamics, given ST and AT, it outputs some ST plus 1. And meanwhile, it also produces a reward function, which tells the agent if the action is good or not, depending on the task. So for different tasks, you have different reward functions that will guide the agent's behavior. So the target of reinforcement learning is to find some policy or controller pi star that maximize a trajectory of rewards. So in this case, you have an expectation over different policy action distributions. And then you are trying to maximize summation from t equals to 0 to capital T, and you sum over all the rewards, and you're trying to maximize this term. And there are just too many algorithms to optimize this objective. Depending on from which angle you are viewing these algorithms, it can be roughly divided by different ways. So depending on if you are going to care about learning the transition dynamics, it can be categorized by model-based RL or model-free RL. The model here is the transition dynamics models. And depending on if you want to only consider learning the policies, or you also want to learning only the value functions, it can also be categorized into policy-based or value-based, or somehow, or some middle ground of these two methods, which is the actor-critic line of work. And depending on what type of data you are going to use, is that the data you use to optimize your policy is that necessarily come from your policy itself or come from other data source. It can also be divided to either on-policy algorithms or off-policy algorithms. And in this lecture, depending on the relationship to the robotics content, also depending on the time, we are only to talk about one class of that, which is model-free actor-critic and on-policy algorithms. The development of that comes from a very straightforward method, algorithms called reinforce. So this is just one example is the game of Pong. So it's an Atari game that there are two players, each of them controlling the board to move up and down. And the goal is always to make the ball pass the other player's board and then going to the edge of the other boundaries. And you will receive negative reward or positive reward depending on why, if you are successfully doing so. So imagine you have some agent, and usually what we nowadays do is having a neural network that directly takes the image input and output some actions. And these actions can simply be, if it's 0, it moves downward. If it's 1, it moves upward. So the one difference between RL and supervised learning is you do not have a very concrete definition of what is the label is. So of course, so there are also, in the next lecture, we might talk about behavior cloning, which you have human label that. But in a more general formulation of reinforcement learning, we want to learning from the reward provided by the environment to guide this policy network to win the game. So the way we can do that is instead of relying on the labels, we can sample a lot of different trajectories by the policy. So imagine you have some policy that randomly initialized at the beginning, and you collect a different trajectories in the environment. So sometimes it gets a sequence of up, down, up, up, down, 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 and it leads to win. And there are also other cases lead to lose. And there are some relative difference between the reward, which tells you which kind of decision is good and which is not good. So this kind of learning signal, we can use that to guide the policy learning and becomes can perform the task better and better. And more mathematical formulation. So this is directly taken from the reinforcement learning class in Berkeley. So we are going to the first equation is essentially the objective of reinforcement learning. We want to find a policy theta, which is a neural network weight that can maximize the expected return. And this is when you actually do not have the expectation, but you only have a set of maybe thousands, hundreds of trajectories. And how you're going to evaluate that is to sum or is average over all these kind of trajectories. And after some very interesting and clever like mathematical derivations, and it turns out it's relatively easy to take a gradient of that objective, and you can get the gradient of the objective is some term very similar to supervised learning term. And as a result, it's also very easy to implement in modern PyTorch libraries. And so the formulation, what makes the formulation interesting is that it's a weighted average of this part. So which is very similar to if you have your supervised learning algorithm and there is not the pi theta, but the neural network predictions, and it's weighted average by the reward functions. So what it says is actually if your reward, for the trajectory you are collecting, if the reward of a certain trajectory is higher, it will make the policy have a gradient towards that trajectories. So after you have iterations over this formulation again and again, the trajectories, like the policy distributions of all possible trajectories generated by the policy will soon convert this to somewhere that can result into a high reward term. And more concretely, if you write the reinforced algorithms, it just simply involves you sample a lot of trajectories according to your network. And then you, according to these formulations, take gradient, and then doing SGD step using some popular optimizers. So reinforce is very straightforward to implement and a basic policy gradient algorithms. However, it also has a lot of problems. And one of the major problems comes from the idea of evaluating performance of different trajectories. So in this step, if we want to have a very stable gradient that is helpful for policy learning, we kind of want the evaluation to be smooth and low variance, which means that if in a current state, if in the same state, we are going to take two similar actions, we want the sum of the rewards to be similar. But the difference in reinforcement learning is that you are taking a long trajectory of different state and actions, and your policy is stochastic instead of deterministic. So even though you have the smooth transitions at the current step, and after you take 100 other steps, the reward might be very different. So this is one of the motivations. The other motivations is actually we don't care about the absolute values of your trajectory reward, because it's very hard to compare what is the reward mean by saying reward is 100 versus 1,000. So what we care about is the relative improvements on a state between two actions. And there are also some other rich literatures on these Q functions, value functions, and action functions. But essentially, we are going to define some kind of fancy terms, so firstly is the Q function, which tells you from the current state, ST, if you're going to take action AT, so what is the goodness of the action AT, and measured by what is the expectation over different rewards after you take the action AT. And value function is value function is defined on top of Q functions, which measures the goodness of the state instead of the actions. So the way it calculates is that you consider all possible actions generated by your policy and evaluate a weighted summation of all of them. And after we have these two quantities, we can define some advantage functions, and which is at the current ST, if you are going to take action, what is the difference between you take this action and you stay as the mean at this state, you take the mean actions at this state. So that's called the advantage, because it's the advantage of the action compared to average actions you can take in this state, in the current state. And compare an actor-critic is really simply just replace this, your summation over the rewards functions over all the trajectories, and you change that term to be the advantage functions. So there are a lot, yes. So there are lots of, also there are a lot of explanations from different aspects on why are you doing this. But I think from my perspective, you are going to learning a neural network that's trying to fit this, trying to get this action function by fitting these value functions. And the advantage is, so firstly, so you can see a lot of different data across this episode. So instead of just, so the value is not only estimate from the current batch of data, you also get a lot of, you also get from the training, from the beginning of the training to the end of the training, you continuously fitting these value functions by using all the data you have. So this is one thing you can, so the value function, by seeing a lot of different data, it can get better estimates on the current state. And also because in this case, you always get a limited number of trajectories. So sometimes if the trajectory is too small, this estimate maybe have very high variance. But if you have a value function, it consider, like for the same reason, you see all of kind of data. So you kind of can get a smooth behaviors just naturally provided by the neural network. So that's the actor-critic, where one missing part is I forgot to mention the neural network learns is the VT here, and the AT, the advantage function can be derived from the reward defined the current step, and plus the value function as the next stem step, and minus the value function as the current stem step. And Actor-critic solves a lot of problems of vanilla reinforce, but there are, like, it increased the training stabilities, it also increased performance. But the problem is, in the development of RL algorithms, people realize policy is very easy to collapse. So collapse means you have keep having very high reward, and and suddenly after you take one extra gradient steps, the performance just drops drastically. And there is a lot of research on this by constraining, maybe saying the policy step cannot be too large by maybe clipping the gradient or clipping the parameters in the parameter space, but they do not work quite well. And finally, and I think empirically, a best working case is the proximal policy optimization method, which is also surprisingly simple. So consider these rather complex expressions. So if you're focusing on the advantage functions, so this is what we maximize in the previous actor-critics. We want to maximize the advantage function along these policy generated trajectories. And it takes a minimum between these terms and these terms. And these terms is defined by the clipping functions depending on if your advantage function is positive or negative. And I'm going to, so this is, of course, the credit comes from this OpenAI blog, but it's also very helpful to understand that. So imagine you have an advantage function that is positive, which means at the current state, you take this action is good. So because this, by definition of the advantage function is the goodness of this action at this current state. So what we have is, firstly, we have this advantage function, and then also we have this one. So pi theta k is the current probability of producing the desired action for the current policy parameter theta k. And this pi theta is something we are going to optimize in the next time steps. And in this case, what we want is the pi theta what we want is to produce a higher probability for action A, because the advantage function is positive. But meanwhile, we also do not want the optimization takes step farther away compared to the current policy because of the policy collapse problem. So what we do is we consider these ratios. We want these ratios to be greater than 1, but we do not want it to be too large. So we will have a clipping term, which is 1 plus epsilon. This epsilon is hyperparameters typically set to 0.1 or 0.2. And then by clipping this to 1 plus epsilon, we usually guarantee that so the difference between two policies is not too large. So you are not taking a very large gradient step that destroy all of your previous policy training. And similarly, is the when the advantage is negative, which means the action here is not so good, and we want the probability of producing these actions to be smaller than compared to in the previous time step. And by the same logic, we want this one to be smaller than 1, but also not so small. And in this case, we are going to have another clipping terms, which guides the policy, to be staying close to the original policy. Okay, so that's the first part. Any questions?
So you're changing K during your training, for example, after you train for 10 steps, then you also update K by like K plus 10. Is that it?
So the theta, I mean, the K is maybe not very meaningful here. So it's just saying this is after theta k, you're going to produce theta k plus 1, which is this theta.
Oh, I see. So this case precisely the policy from the previous step.
Yeah. Okay. And next, we are going to talk about attempts to applying RL to robotics. And if you think about maybe the first time I saw this formulation of Markov decision process, I think it's a very natural choice to consider this agent to be a robot that interacts with our environment. And of course, this is indeed have been well started for more than 40 years that using RL for robotics. But maybe a key moment in this whole development of whole deep RL is the success of DQN in 2015 and AlphaGo in 2016, where essentially the DeepMind researchers firstly showing you can applying these DQN algorithms to achieve continuous like human level continuous control in different Atari games. It's not only one games, but like a lot of different games under one single formulations and do not have too many tricks, still have some tricks, but it's still general enough to cover a wide range of games. And also the AlphaGo in 2016, which is roughly when I started research. So they apply this problem on Go, which is traditionally people think the search space is too large for any algorithms to be feasible. And I think these two events really triggers people's interest on using RL for something, because maybe like the search space of in some tasks, the search space of robotics manipulations is not so large. And also there are also like contributions from the simulator side, which including OpenAI Dream and DM control. They define a set of different continuous control tasks in the context of robotics. And also the greatest contribution here is so they define a very good interface so that you can focusing on developing your RL algorithms instead of considering you need to deal with also the bottom level simulators. You can only so you can do this research by writing Python code on simple algorithm terms instead of need to considering, oh, how should I define these models and how do I communicate with different C++ code? And all of them greatly increase the interest on using RL for robotics. So of course, RL is keep increasing, but it's just significantly increases like in very recent years. So when we consider applying RL to robotics, there are definitely two categories. So first one is you can run your RL algorithms directly in the real world, in your real robot, and receive the interactions from the environment. And another way is to use sim-to-real. And I'll describe them one by one. So here is a video of real-world RL. So real-world RL is it's very promising in terms of that you can, after you have this setup, you can leave it there and it automatically improves according to your reward functions. And so this is one of the examples I found pretty interesting. This is a quadruped learning to walk guided by the reward terms purely in real world. I'll play it for a while. So this is after maybe 1 or 2 hours of trials. No. Yeah, after that, it learns pretty decent robustness and also maybe a little bit generalization to different environments. So that's a like pretty good result in real world RL. And there are also, of course, challenges and hot research topics in real world RL. So for example, RL is very well known to be sample inefficient because you rely on trial and errors to collect a lot of samples and also and then optimize your policy. So therefore, a very large portion of research focuses on sample efficient RL, which is, so you might see that people doing some new RL improvements on OpenAI Gym or the DM control that achieving some promising control tasks within millions of samples. And how the other challenge is about the unsafe. So in the context of robotics, directly deploying this real-world RL is not very safe. So in the previous example, if you view it carefully, so initially, so the robots need to be constrained on some certain kind of very small motions. So you cannot give a very high velocity or high amount of force because the hardware may maybe break. And also there are also problem, I mean, which I think is a very important problems on real world RL, which is to rely on human labors to reset the environments. So in the previous video, if you remember, so there is always a human that moves the robot from the end positions to the beginning of the positions. So every time step, a human need to do that. And there are also another aspect is how are you going to define reward in the real world? So this is, imagine walking is a very, like semantically, is a very well-defined task. But if you want to measure the progress of walking, you need to have an accurate detection on what is the position of the robot. And it might be okay if you are working in indoor environments, you have a like calibrated camera for detecting these objects. But if you are going to consider deploying this, real outdoor environment, so that is pretty hard. So computer vision at that time is not super good to achieve that. And here are other examples of just giving some examples. So there are also learning real world RLs to rotate this valve. And to rotate this valve, we also need a detector on what is the position and orientation of the valve. And what they did is to place some sensors on the end of the some instrumental on some other equipment to get the orientation of the valve. And also this is a robotics opening a door experiments, and they need to have some automatic reset process, which is some mechanical structure that automatically close the door. So these types of examples kind of need to design for each kind of different task. So this is pretty labor intensive. And on the other hand, compared to real world RL, is you can do sim to real. And the advantage is kind of the opposite of the disadvantage of real world RL. So reward is very easy accessible from simulations. So in simulation, all the velocities and positions is well defined, and then you can just get that from one line of code. Reset is also very easy because at each episode, you will just assign what is the positions and orientations of the objects. But the problem and the challenge of sim to real is also the opposite of real world RL, which is after you learning these policies in simulation, there is always a sim to real gap between your policy trained in simulation versus deployed in the real world. And sim to real in 2018, 2019, so there are also a lot of attempts. And there is even a very hot debate on if we should still invest in sim to real. There's a workshop in RSS, so there is a very interesting term called sim to none, which is people work too much on simulations and claim their algorithms is better by comparing different simulation benchmarks, but none of them can transfer to the real world. So this is basically sim to none. And what makes this more worse for RL to robotics is not only the problem of robotics, but also the problem of RL. So this is also a famous article when I started to looking at RL. So I forgot to take the reference, but this is from Mila, and I think it's called Deep Reinforcement Learning That Matters. So the set fact at that time is, so this is two learning curves, and this two learning curve is produced by, so you having some TRPO, some policy gradient algorithms running on a certain locomotion tasks on OpenAI Gym. And so in the first trial, you randomly sample 5 different random seed and run your algorithms. So it produces this curve. And next time you randomly sample another 5 different random seed, and then you get a curve like this. So this is not a cherry pick 5 random seed. This is really 2 set of randomly chosen seed. So even in this case, your policy will still have a reasonably gap, which indicates that if you see a curve that improves in the paper, it might not be like truly improvement. It may be just the seed is better. And also there are a lot of other factors, which is the code base different. So there are a lot of very small engineering choice that will make your policy either stability-wise or performance-wise to be very different. So this is small implementations that are all of them are considered correct, but there are also some small difference in terms of design choices, and implement the same algorithms on the same environments, and the learning curve is significantly different. And some other examples, including, so this is typically RL training curves, which goes to absolute returns goes to very high and very stable. And when people are happy with that, it suddenly goes to very unstable stages. And in comparison, if you are training computer vision networks, this is very stable. So the training curves, of course, because of stochastic batch gradient descent, you have some slightly up and down. But after that, the general trend of your training still remains the same. So, so at that time, people will tend to think it remains significantly challenging to apply RL to robotics, and people don't know how to deal with not only the challenges from robotics, but also the challenges from reinforcement learning themselves. And so especially on complex systems such as hands or legs, there are really limited number of success examples. And so I think the major rebirth of this line of work is driven by sim-to-real. And of course, there are also other success examples, but maybe the experiments that bring people's attention to this back again is driven by sim-to-real. And before we delve into what work exactly does this work do, we will then take a small detour from reinforcement learning and talk a little bit about basic concepts in simulators. Before that, any questions regarding the previous sections? Okay, and as we have already seen in previous sections, the simulation are kind of widely used in RL research. So, for example, the OpenAI Gym or the DM controls, and people use simulators usually in 2 different ways. So they can use simulators to develop an algorithms. So either it can be RL algorithms or even model-based control algorithms. And then what people want to get from simulators is to get a sense of what type of algorithms works and what is a good set of hyperparameters. So after people debugging and developing algorithms and finding a good set of parameters, they can directly run these algorithms in the real world. So the simulation data is used to tune your controller instead of get a model for that. And on the other hand, there are also people using actually the simulator data to train your model and deploy these models to the real world. And one distinct fact between these two is in the later stage, the point is not sample efficient anymore. So because as we will see in the a little bit later slides, so the current simulators runs very fast and you do not need to worry about, oh, my algorithms need like hundreds of millions of samples to get a stable state. So sample efficiency still helps when in the iteration speed in terms of between your developing algorithms trying to deploy and get a new model, it helps in this process. But the more important thing here now becomes how stable is your training and what is the performance of your algorithms. Okay, simulators. And here is an overview, very simplified overview of rigid body simulations. This slide is credited to the PyBleed team. So the simulation loops run over forward dynamics and numerical time integrations and collision detections. So in time integrations, you are given the accelerations of different rigid bodies, given the force, and you have some algorithms or techniques to update the velocities and the positions of all the rigid bodies in your environments. And in certain cases, actually in many cases, there will be collisions between either two rigid bodies or your rigid body and the environments. And then in this case, there will be techniques to detect and resolve these collisions. And after that, after this step, you will get updated velocities and positions of all the objects. And then you will compute the accelerations and forces again, and for the time integration. So this is running in a loop defining on what is your episode length and what is your time horizons. So for the, let me see. For the forward dynamics part, so the forward dynamics is a process that given positions and velocities, and we want to calculate accelerations of the different rigid bodies. So in the simplest case, if you consider you only have a point mass, you can calculate that by just using F equals to ma. But in a slightly more complex case, you have a rigid body that involves orientations and angular velocities. You need to use these equations to get that. So the tau equals to, so the I here is the initial matrix depending on the mass distributions of your objects. And the omega dot is the acceleration of your angular velocities. And there is another term which makes it looks different from the F equals to ma, which is really consider when you have a rigid body that rotates, it does not always follow the same rotation axis. And the rotation axis may not pass into your center of mass. So there need to be some extra term derived from physics for that. And after that, you can calculate the updated velocities and updated positions according to these few equations. But there are also something I haven't mentioned, which is at some point there will be external force and the force from contact at this executed at this time step. And the external, so you can essentially divide it by, you have the effect of external force applied to the objects. Also something which we call the impulse that is produced by the contact, which I'll describe in a 3 slide later. So this is for the motions. So how you get accelerations for rigid bodies. In robotics, we care more about getting not only a single rigid object, but it's a linked rigid body, which is a multi-body interactions. So consider you have a robot arm and have 7 degrees of freedoms. And this robot arm is the robot arm is essentially having 7 different links, and they are connected by a joint. And the physics becomes quite complicated if you write that into Newton's formulations. And this is and we have some tools for that, which is called Lagrangian dynamics. In the last lecture, we also talked about a little bit of that. But in this case, what we are so a few concept is when we talk about generalized coordinates in manipulation, it really just means you have these revoluted joints and you have maybe 7 joints, and then each of the joint angles is the generalized coordinates. So you have the 7 joint angles, then the configuration of your robot arm is uniquely defined. So that's the coordinates of your robot arm. And kinetic energy and potential energy are also defined same as in the physics. And generalized force, and in this limited robot arm manipulation examples, it only means how much torque you applied on each of the joints. So the formulation is, say, if you write down the kinetic energy and potential energies and take a derivative of the L, so the L is T minus U. So you can get the formulation of what is the torque on each of the joints. And the torque is essentially the accelerations of the rotations. And one example, so you can see a very complicated equations, but take into account that you have a simulator and all this mass and length and all these kind of values, including M and L, and also the Q dot, which is the velocities, and Q dot and Q is the velocity and positions of the objects. So all of them are known. They are just single scalars defined by either your URDF or the velocity positions returned by your simulators. And it's kind of easy to get a relationship between the Q double dot and the torque you applied on the joint. So given this, is really, so remember our purpose is to get accelerations of different joints. And according to your external control input. So in this case, all the other quantities is known, and we can get a relationship between accelerations and the control input. So this is how at each time step you updated your angular velocities, and then as a turn change to your velocities and also your positions. And after that, there will be, after you get the updated position and the velocities, there will be also a stage of collision check. So the idea of collision check is simply, there are 2 phases. The first one is the broad phase, and also there is another one, which is a narrow phase. Broad phase is simply if you consider 2 convex objects. If the 2 convex objects are too close to each other, they will be considered possibly can collide with each other. And because this is very broad, you can just calculate that by comparing first the distance between center of mass, also consider the shape of the objects. So what is the closest point between 2 rigid objects? And for the narrow phase, there are rich literatures on that, and there are also well-established algorithms to implement that. And this may be rather very complicated, and we are not going to introduce in this class. But if you're interested, you are welcome to check these algorithms. So usually that's very sophisticated that you need to, between 2 time steps, you need to consider a lot of things. For example, if there are 2 small objects moving in very fast velocities, if you directly consider the positions in the current time step and the other time step, they may just penetrate with each other without knowing they actually penetrate. And there are a lot of techniques to actually capture that collisions and resolve that collisions. And there are also important concepts of, in real world, we do not always have convex objects. And when we have a complex objects in the real world, if we want to model a rather complex object in simulations, we also need to decompose that into a lot of composition of primitive convex shapes. So this is one convex decomposition method, which is HACD. You can use optimization method to run on each kind of vertices. What is the possible way that satisfy convexity together with being as close as the original not convex shapes. And also, this is how the simulator resolve collisions. Again, this derivation is a little bit complex. And the point in this figure is to saying, in collision detection, we are actually doing this. So if you updated the position and velocities and find there are some penetration between two different objects, so what we could do is to apply in some force represented by the contact that trying to move these two parts away. So in the contact point, we can apply the impulse according to how much between two objects penetrates, and then what is the velocity between the two objects. And we doing that for several iterations until some constraint is satisfied. So the constraints can be, you have two objects, they are not penetrated with each other, and they are also as close as when they are having these contacts. And this is the correction term, which related to a few different quantities, such as the mass of two objects, also the initial matrix of the two objects, also the R and N defined as is uniquely defined by the contact points. Okay. I think we will break here, and after we have the break, I will starting to talk about some examples of the simulator we can use for robot learning.